Oscillation. In this module, we will be learning about oscillatory motion in detail. But before going any further, let us define a few terms. Periodic motion. A motion which repeats itself after a fixed interval of time. Let us take some examples of periodic motion. Motion of the moon around the earth is a periodic motion as it repeats itself after a fixed interval of time. Motion of the hands of a clock is also a periodic motion as it repeats itself after a fixed interval of time. The heartbeats in our body also represent a periodic motion, as they repeat themselves after a fixed interval of time. Also, a child swinging on a swing is an example of a periodic motion, as it repeats itself after a fixed omega t plus phi naught. OP prime is equal to x t is equal to a cos omega t plus phi naught. Equation 1. Where a is equal to amplitude, omega is equal to angular frequency, t is equal to time, phi naught is equal to phase constant. The motion represented by equation 1 is called simple harmonic motion or SHM, a term that means the periodic motion is a sinusoidal function of time. Here, phi naught is the angular position of point at t is equal to 0. So, in simple harmonic motion, displacement is sinusoidal function of time. It is very important to understand that non-harmonic oscillation is a combination of two or more harmonic oscillations. Geometrical interpretation of simple harmonic motion. Particle P, or reference particle, goes around the circle and completes one revolution. The projection M moves to and fro about the center O along diameter y prime OY. Motion of projection M on a diameter YOY prime is called simple harmonic motion. Simple harmonic motion is defined as the projection of uniform circular motion on the diameter of a circle of reference. Where a is equal to radius of circle, omega is equal to angular velocity, theta is equal to angle, t is equal to time, and y is equal to displacement. In triangle OPM, sin theta is equal to OM upon OP is equal to y upon a. Y is equal to a sin theta is equal to a sin omega t. Here, theta is equal to omega t. Consider the particle has some phase, phi naught, initially. Y is equal to a sin omega t plus phi naught. Here, theta is equal to omega t plus phi naught. Amplitude. Maximum displacement on either side of the mean position. Here, maximum value of y is a. Velocity and acceleration in simple harmonic motion. Let us find out the equation of velocity of a particle undergoing simple harmonic motion. Velocity. The instantaneous velocity of a particle executing simple harmonic motion can be obtained by differentiating displacement with time t. Equation of particle in simple harmonic motion is xt is equal to a cos omega t plus phi, equation 1, where a is amplitude of displacement. So, Vt is equal to d upon dt xt is equal to d upon dt a cos omega t plus phi. Therefore, Vt is equal to minus omega a sine omega t plus phi. Omega a is the amplitude of velocity. The negative sign appears because the velocity component of p is directed towards the left in the negative direction of x. Acceleration. Now let us find out the equation of acceleration of particle undergoing simple harmonic motion. We have seen that a particle executing a uniform circular motion is subjected to a radial acceleration a directed towards the center. To obtain acceleration of a particle executing simple harmonic motion, we have to differentiate velocity Vt with time t. At d upon dt Vt. On solving, we find that At is equal to minus omega square a cos omega t plus phi is equal to minus omega square xt. This is the acceleration of the particle p prime. The projection of particle p on xox prime. Thus, simple harmonic motion may be defined as that periodic motion in which acceleration is directly proportional to the displacement from the mean position and is always directed towards the mean position. Force law for simple harmonic motion. According to Newton's second law of motion, force Ft is equal to ma, where m is mass and a is acceleration. In case of simple harmonic motion, we have acceleration a is equal to minus omega square xt. So, therefore, Ft is equal to ma is equal to minus omega square xt is equal to minus kxt. Let us label this as equation 1. Therefore, k is equal to m omega square. Omega is equal to under root k upon m. Equation 1 gives the force acting on the particle. It is proportional to the displacement and directed in an opposite direction. Therefore, it is a restoring force. The restoring force for simple harmonic motion is time-dependent. Energy in simple harmonic motion. Let us find out the energy of the particle in simple harmonic motion. Kinetic energy, Ek of a particle in simple harmonic motion is given as Ek is equal to 1 upon 2 mv square. From the equation of velocity we get Vt is equal to minus omega a sine omega t plus phi. Now, combining both the equations, we get Ek is equal to 1 upon 2m omega square a square sine square omega t plus phi is equal to 1 upon 2 ka square sine square omega t plus phi. Now, potential energy, Ep of a particle in simple harmonic motion is given as E is equal to 1 upon 2k x t whole square is equal to 1 upon 2 ka square cos square omega t plus phi. Therefore, total energy of the system in simple harmonic motion is given as E is equal to Ek plus Ep, which is E is equal to 1 upon 2 ka square sine square omega t plus phi plus 1 upon 2 ka square cos square omega t plus phi. On simplifying it further, we have E is equal to 1 upon 2 ka square sine square omega t plus phi plus cos square omega t plus phi is equal to 1 upon 2 ka square. In this equation you can find there is no term involving time t. Hence, from the above equation we find that the total mechanical energy of a harmonic oscillator is independent of time. As expected for motion, under any conservative force. The time and displacement dependence of the potential and kinetic energy of a linear simple harmonic oscillator are shown here. Oscillations, spring, pendulum. Oscillations due to a spring. Oscillations of a block of mass m fixed to a spring, which in turn is fixed to a rigid wall. The block is pulled and released so that it executes to and fro motion or simple harmonic motion. Here, m is equal to mass of the block plus a minus a is equal to maximum displacement. X is equal to 0 is equal to position of the center of the block at the equilibrium of the spring. When the spring is deformed, it is subjected to a restoring force Fx, which is proportional to the displacement x in the opposite direction. Fx is proportionate to minus x. Therefore, Fx is equal to minus kx. Equation 1. K is the spring constant, which depends on the property of the spring. Using Newton's second law of motion, the force applied to pull the spring, F is equal to ma, which must be equal and opposite to the restoring force. Since acceleration in SHM is equal to minus omega square x, therefore F is equal to minus m omega square x. On comparing it with equation 1, Fx is equal to minus kx, we get k is equal to m omega square. Omega is equal to root k upon m, where omega is the angular speed of the spring. Time period t of the oscillator is t is equal to 2 pi upon omega, or t is equal to 2 pi root m upon k. Simple pendulum. A simple pendulum is a heavy point mass suspended by a weightless, inextensible, and a perfectly flexible string from a rigid support about which it can vibrate freely. Periodic motion of a simple pendulum for small displacements is called simple harmonic. M is equal to mass of the bob. L is equal to length of the massless string. Theta is equal to angle made by the string with the vertical at any instant. T is equal to tension along the string. G is equal to acceleration due to gravity. Radial acceleration is equal to omega square L. Net radial force T is equal to mg cos theta. Tangential acceleration is provided by mg sin theta. Torque tau is equal to minus mg sin theta L. According to Newton's law of rotational motion, tau is equal to I alpha, where I is moment of inertia. Alpha is angular acceleration. Therefore, I alpha is equal to minus mg sin theta L. Therefore, alpha is equal to minus mgl sin theta upon I, equation 1. We know that sin theta is equal to theta minus theta cube by factorial 3 plus theta raised to the power 5 by factorial 5 and so on, where theta is in radian. Theta is kept very small, about 4 to 5 degrees. Ignoring the higher power of theta, we get sin theta is nearly equal to theta. Substituting sin theta is equal to theta in equation for angular acceleration, alpha is equal to minus mgl sin theta upon I. We get alpha is equal to minus mgl upon I theta. Equation 2. On comparing it with alpha is equal to minus omega square theta, we conclude that the motion of a simple pendulum swinging through small angles is approximately simple harmonic motion. Now, substituting alpha is equal to minus omega square theta in equation 2, we get omega square theta is equal to mgl upon I theta, or omega square is equal to mgl upon I. Angular frequency omega is equal to root mgl upon I. We know that time period t is equal to 2 pi upon omega. T is equal to 2 pi under root I upon mgl. On substituting I is equal to ml square, we get T is equal to 2 pi under root L upon G. Time period of simple pendulum is directly proportional to the square root of its length. T is proportionate to root L. Damped simple harmonic motion. In this module, we will learn about damped simple harmonic motion. Damped simple harmonic motion can be simply explained with a mass connected with spring and a block system. A vane is connected with the block, which remains submerged in water as shown. You will notice that as the block oscillates up and down, the displacement on graph reduces with time. Thus, a simple harmonic system that oscillates with decreasing amplitude with time is called damped simple harmonic oscillation. Some very important points regarding damped simple harmonic motion are that in damped simple harmonic motion, the energy of the system is dissipated. That is, the damped simple harmonic system constantly loses energy. Damping force Fd, which damps the oscillatory motion, depends on the nature of the surrounding medium. It is proportional to the velocity v of the block and acts opposite to the direction of velocity of the block. That is, Fd proportional to minus v. Fd is equal to minus bv, where b is equal to positive constant, depends on characteristics of the medium such as viscosity, the shape, and size of the block. It is very important to understand that when a mass m attached to a spring is released, it settles to a height. When the mass is pulled up or down, the restoring force Fs on the spring is proportional to the displacement x from its equilibrium position. By equation, Fs proportional to minus x, or Fs is equal to minus kx, where x is the displacement from the equilibrium position and k is the spring constant. Let us combine both the equations. Now, according to Newton's second law of motion, net force acting on the body is equal to damping force plus restoring force, which is equal to ma into t is equal to minus kx into t minus bv into t from the previous equations, which in turn becomes m d square x upon dt square plus b dx upon dt plus kx is equal to 0. On finding the solution to the equation, we get x into t is equal to a into e raised to the power minus bt upon 2m cos omega prime t plus phi. Here, a into e raised to the power minus bt upon 2m is the amplitude. Omega prime is equal to angular frequency of the damped oscillator. Omega prime is equal to whole under root k upon m minus b square 4m square. It is very important to note that x into t is equal to a into e raised to the power minus bt upon 2m cos into omega prime t plus phi is not periodic because e raised to the power minus bt upon 2m decreases continuously with time. Hence, the amplitude keeps on decreasing with time. The mechanical energy in the damped system is represented as E is equal to 1 upon 2 Ka square e raised to the power minus bt upon m. The equation shows that the total energy of the system decreases exponentially with time. It is important to note that for small damping, b upon under root 2 km much less than 1. Forced oscillations and resonance, Part 1. Let us now understand about forced oscillations and resonance. Forced oscillations and resonance can be explained by a spring attached with a ball and a hand on the other side. Now, if the ball goes up and down, the oscillations die out with time due to damping. However, if the hand also goes up and down along with the ball, this external force of the hand gets applied to the system and now the ball starts oscillating without dying out. An associated term with forced oscillations and resonance is called as natural frequency. Let us learn about the terms related to forced oscillations and resonance. If no external force acts on a system, the system will execute oscillations of frequency nu naught. That is called as natural frequency. The oscillations produced under the effect of an external periodic force of frequency other than the natural frequency of the oscillator are called forced oscillations. If an external force Ft is applied to a damped oscillator, then Ft is equal to F naught cos omega dt. Let us label this as equation 1, where F naught is equal to amplitude of external force, omega d is equal to driven frequency. The motion of a particle under the combined action of a linear restoring force, damping force, and a time-dependent driving force, as represented by equation 1, is given by MAT is equal to minus KXT minus BVT plus F naught cos omega dt. M d square x upon dt square plus b dx upon dt plus kx is equal to F naught cos omega dt. Let us label this as equation 2. The displacement after the natural oscillation dies out is given by xt is equal to a cos omega dt plus phi. Amplitude A is the function of the forced frequency omega d and the natural frequency omega. Forced oscillations and resonance, Part 2. Analysis shows that amplitude is given by A is equal to F naught upon square root m square omega square minus omega d square whole square plus omega d square b square. Let us label this as equation 3. Tan phi is equal to minus v naught upon omega dx naught, where m is equal to mass of the particle, v naught is equal to velocity of the particle at t is equal to 0, x naught is equal to displacement of the particle at t is equal to 0, omega is equal to natural frequency. Let us take some cases. Case 1. Small damping, driving frequency far from natural frequency. In this case, omega dB will be much lesser than m omega square minus omega d square. Omega dB less than m omega square minus omega d square. Therefore, A is equal to F naught upon m into omega square minus omega d square from equation 3. Case 2. Driving frequency close to natural frequency, or omega d is very close to omega. M omega square minus omega d square would be much lesser than omega dB for any reasonable value of b. M omega square minus omega d square less than omega dB, then the equation 3 reduces to A is equal to F naught upon omega dB. The amplitude is greatest near omega d upon omega is equal to 1. The 5 curves correspond to different extents of damping present in the system. Curve A corresponds to the least damping, and damping goes on increasing successively in curves B, C, D, and E. Notice that the peak shifts to the left with increasing B. The phenomenon of increase in amplitude when the driving frequency is close to the natural frequency of the oscillator is called resonance. Resonance. Now let us learn more about the phenomenon of resonance. In the previous module, we have learnt about the phenomenon of forced oscillations and resonance. The phenomenon of increase in amplitude when the driving frequency omega d is close to the natural frequency omega of the oscillator is called resonance. The amplitude is greatest near omega d upon omega is equal to 1. Here we have a set of 5 simple pendulums of assorted lengths suspended from a common rope as shown. Every pendulum has a natural or resonant frequency, which is the number of times the pendulum swings back and forth per second. Time period of simple pendulum is directly proportional to the square root of its length. T is proportional to root L and nu is equal to 1 upon T. Longer pendulums will have lower frequencies, since frequency is inversely proportional to time. Here you can observe that the pendulums 1 and 4 have the same lengths and the others have different lengths. Now let us set pendulum 1 into motion. The energy from this pendulum gets transferred to the other pendulums through the connecting rope and they start oscillating. The driving force is provided through the connecting rope. The frequency of this force is the frequency with which one pendulum oscillates. We observe that pendulums 2, 3 and 5 first start oscillating with their natural frequencies of oscillations and different amplitudes. But this motion is gradually damped and not sustained. Their frequencies of oscillation gradually change, and ultimately they oscillate with the frequency of pendulum 1. That is, the frequency of the driving force, but with different amplitudes. They oscillate with small amplitudes. The pendulum 4 oscillates with the same frequency as that of pendulum 1, and its amplitude gradually picks up and becomes very large. A resonance-like response is seen. This happens because in this the condition for resonance is satisfied. That is, the natural frequency of the system coincides with that of the driving force.